Hello students, you are welcome to today's lecture on current electricity. In our daily life, we use electricity for various activities such as the lighting of electric lamps in our houses, playing of music on tape recorder, listening to radio programs, watching of different programs on television, and the cool breeze we enjoy from electric fan or air conditions. This means that the study of electricity cannot be overemphasized in our modern world. At home, you might have observed that as soon as you switch on an electric lamp, it starts glowing. Why does it happen? What role does the switch play? You shall be able to answer these questions after this lecture. Remember, in study session 5 and 6, you have learned about electric charges at rest and forces between them, which constitutes one aspect of electricity called static electricity. However, in this study session, you will learn about another aspect of electricity which deals with movement of electric charges. This aspect of electricity is referred to as current electricity. The learning outcome for study session 7. When you have studied study session 7, you should be able to define the term electric current, describe series and parallel arrangement of cells, describe series and parallel arrangement of resistors, state Ohm's law and applies this law to solve circuit problems, define resistance, resistivity and conductivity of metallic material, and use their formula in solving circuit problems. From these learning outcomes, we are going to concentrate on the first two learning outcomes in this part. Electric current. In the previous lectures, you have learned that when a potential difference is applied across conductor, an electric field is set up within it. The free electron moves in a direction opposite to the field through the conductor. This constitutes an electric current. Thus, an electric current could be defined as the rate at which electric charge flows, at which electric charge flows, and it is mathematically represented as I is equal to charge Q divided by time T, where I is the electric current measured in ampere. Note, 1 ampere is equal to 1 coulomb per second, and Q is the amount of charge passing through a given area measured in coulombs. T is the time it takes the charge to flow from one point to another, and it is measured in seconds. Conventionally, in an electric circuit, the direction of current is taken as the direction in which a positive charge moves. Now, let us solve questions on how to determine any of the parameters in the equation of electric current. Example 1. What is the current involved when a truck battery sets in motion 720 coulomb of charge in 4.00 seconds while starting an engine? Solution. In example 1, the given parameters are charge Q, which is equal to 720 coulombs, and time T, which is equal to 4.00 seconds. From the question, the unknown parameter is current I. In order to obtain I, because current I is equal to charge Q divided by time T. Therefore, I equals to 720 coulombs divided by 4.00 seconds, which is equals to 180 coulombs per second, or simply 180 ampere, since current is measured in ampere. Now, it is time for you to test your knowledge of understanding of concept of electric current. Now, answer the question. Exercise 1. How long does it take 1.00 coulomb of charge to flow through a hand-held calculator if a 0.3 milliampere current is flowing? Note, 1 milli is equal to 10 raised to the power minus 3. Exercise 1b. If the total number of electrons passing through a cross-section of a conducting wire per second are 5.0 times 10 raised to the power 10 electrons, what is the value of current in the wire? Note, 1 electron is equal to 1.6 times 10 raised to the power minus 19 coulombs. you have attempted the exercise, compare your answers to the correct answers given at the end of this lecture. If you have any misunderstanding, refer to the example 1 given here. Now it is time to talk on electric circuit. What is a circuit? The path followed by flow of electric charge is called, the path followed by flow of electric current is called a circuit. There are basic components of an electric circuit. One of the components that can be found in an electric circuit is a resistor. And what is a resistor? Resistors are conductors that have resistance, and the term resistance could be defined as the measure of how easily current flows through a material. Resistor is denoted by capital letter R with different symbols as shown in figure 2. The unit of resistor is ohms. Another component of an electric circuit is a cell or connection of cells called battery, as shown in figure 3. A complete circuit carrying a steady current must contain a source of electromotive force known as EMF, which drives charge out a source from a negative terminal to that of a positive terminal, as shown in figure 1. A cell V does act as a source of electromotive force in an electric circuit. The EMF of a cell or battery is the potential difference between its terminal when current is not flowing in the circuit, that is when the circuit is opened, and it is measured in volts. Mostly, the source of EMF in an electric circuit is a battery, which is a term used for collection of cells, as shown in figure 3. Note, a cell is a single unit of an electric battery. Now, we now talk on arrangement of cells. Basically, there are two types of cells arrangements, which are parallel and series arrangements. The series arrangement of cells are common in flashlights, toys, and other appliances. Usually, the cells are in series in order to produce a larger total EMF. There are general characteristics of series arrangement of cells, and which are: 1. The positive terminal of one cell is connected to the negative terminal of the next cell, and so on. Also, the total EMF of the battery is equal to the sum of the EMFs of the individual cells. Another characteristic of parallel series arrangement of cell is that the current in each cell and in the external circuit have the same magnitude. Also, the total internal resistance of the battery is equal to the sum of the internal resistances of the individual cells. Lastly, the greater potential difference, known as PD, are obtained when cells are joined in series. Another point you should note about series connection of cells is that if the cells are arranged in opposite directions, such as negative terminal connected to negative terminal of one cell connected to the negative terminal of another cell, then the effective potential difference of the arrangement will be 0 if the two cells have the same potential difference. However, if the voltage of one cell is greater than the voltage of the other cell, the effective potential difference will be the difference between the two potential differences. The disadvantage of series arrangement of cells is that their internal resistances, denoted by small letter r, add up together. These sometimes are problematic. For example, if you place a two 6-volt batteries in your car instead of the typical 12-volt single battery, you will be adding both the EMFs of the cells and the internal resistances of each of the batteries. You would therefore end up with the same 12-volt EMF, though the internal resistance would then be doubled, causing issues when you want to start your car. That is, the car engine will experience delay before it starts. This is as a result of high resistance, which resulted to decrease in current that flows through the electrical component of the car engine. Now we talk about the second arrangement of cells, which is parallel arrangement of cells. In parallel arrangement of cells, all the negative terminals are connected together at a point. Also, all the positive terminals are connected together at another point of the circuit. there are general characteristics of parallel arrangement of cells, which are: 1. The total EMF of the battery is equal to the EMF of the separate cells at any moment. For a battery of identical cells, the reciprocal of the total internal resistance, which is 1 over R subscript T of the battery, is equal to the sum of the reciprocals of the internal resistances of the cells. Now, let us solve questions on series and parallel arrangements of cells. Example 2. What is the effective potential difference in the cells arrangements shown in figures A and B? Solution. In figure A, the two cells are in series with positive terminal of the first cell connected to the positive terminal of the second cell. Therefore, the effective potential difference ET equals to difference between the EMF of the two cells, which are E2 minus E1, which is equal to 20 volts minus 15 volts, which is equal to 5 volts. In figure B, the two cells are identical and they are in parallel with the positive terminal of the first cell connected to the positive terminal of the second cell and their negative terminals connected together. Thus, the effective potential difference of this arrangement is equal to 1.5 volts. Now it is time to test your knowledge of understanding of arrangement of cells in an electric circuit. Exercise 2. By considering the circuit diagrams A, B, and C on this slide, what is the effective potential difference in the cells arrangements of each of these circuit diagrams? Note, after completing this exercise, compare your answers to the correct answers provided at the end of this lecture. If you made one or more mistakes in answering these questions correctly, you need to review arrangement of cell section and solutions to questions in example 2. Thereafter, try this exercise again. Now we have come to the end of this part. Thanks for listening. I hope to meet you in part 2 of this lecture, which focuses on arrangement of resistors. Bye for now.